Hello everyone, welcome to the platform of Unacademy and top educators to prepare for your aspired examinations. So I welcome you all. Let me just check it. So, so once again I welcome you all to this session of Vapor Power Cycle. In this session that we are going to see the first part. This is the first part of the Vapor Power Cycle that we are going to deal, which is very important for the GATE and for the ESE point of view. Each and every year, approximately 2 to 3 marks or 4 marks questions are asked from the GATE as well as ESE. ESE has this subject is a lot of importance in the ESE. So today that we are going to see these things in this session. So this is a brief introduction about myself. My name is Vidyapati Kumar and I have a 4+ year of teaching as well as R&D experience. I have done ME from Jadavpur University. I have worked at CSIR Central Institute of Mining and Fuel Research. I have qualified GATE twice, and I'm the author and co-author of various research papers which has been published in international and national journal of repute. So if you have a keen interest about the research works, feel free to research about me, feel free to Google about me and study my research works. Now, this is the first session that we are going to take for the vapor power cycle, which is a part one. And in this, we are going to start our journey of the vapor power cycle, and we will try to understand how the vapor domes are there and how the vapor power cycle operates, what is the significance of the ranking cycles, and how these things are going to help us for the GATE and ESE preparations. So you should download the Unacademy Learning app, because in Unacademy Learning app, by downloading the Unacademy Learning app, you will be able to get the free classes. You can do the free classes at Unacademy Learning app, and there are the paid classes also there. So for a paid classes, it means that you have to go for a plus subscription. But each and every educator publishes the free classes, and the free classes I'm teaching strength of material in the free classes, free lectures. Already I have covered like two modules. First module was stress and strain, and the second module is principal stress and principal strain. So you should download the Academy Learning app, because you are able to prepare for your examinations, and daily live classes are there. You can attempt daily live classes, as well as courses are structured in manner that are there in chronological order. You can attempt a lot of live tests, quizzes and mock tests. A lot of things are there to explore in this beautiful app. As well as this app has the unlimited access of the course content, so feel free to play with the contents. Now, if you are planning for a plus subscription, you are most welcome to do the plus subscription, because it is worth it, because 100% coverage of the syllabus would be there. Okay, so 100% of the coverage of the syllabus would be there at the plus subscription. If you are doing the plus subscription, then you will be able to cover your syllabus of 100% accuracy, as well as one plus subscription gives you the benefit of GATE as well as benefit of ESE, right? So with the one subscription, you can have these two examination preparations. Okay, so again, daily live classes are there. You have in this plus subscription, there are a lot of educators, a lot of good and great educators are there. You can explore a lot of contents from them, as well as I am also there, so you can also explore the great contents from all of us. So all the educator fraternity helps at that at plus subscription. Now, These are the top educators of the Unacademy, and Unacademy has a lot of batches, like batches for different courses, as well as for the different branches of the engineering, like the mechanical, electrical, ECE, CS, IT, production, civil, and so on and so forth. So if you are planning for a plus subscription, definitely you should go for a 1 month, or for a 3 month, or for a 6 month, or for a 12 month, based upon your convenience and eases. So based upon your ease, you are most welcome to go for the subscription. If you think that 6 month is enough for me, then you should go for it, but it will cost around 20,000. But if you will use my code SIRVK, then you will get a 10% off. And 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 with 10% off, you will be having a discounted amount of 22,500. Yeah, you have got a 10% off, as well as I'll provide my mentorship to you. So earlier it was 25,000, now it is 22,500. So you should go for these plus subscription, because the cost is increasing, as the Unacademy will officially tell everyone that cost is increasing. So these things are there. If you are planning for them, you go for this. And if you are in second or third year or fourth year, you should do go for a 24 months plan that would cost around 30,000. But if you will use my code SIRVK, SIRVK, then you will have a 10% off, and the discounted amount would be 27,000. So this is what is cost. If you are planning for a plus subscription, go for it. It is really worth it. It is really worth it. It has the worth. Okay. Good afternoon, Asis. Good afternoon, Subham Raj. No, Subham Raj, for a preliminary thing, Subham Raj, as you know, as you are doing my all lectures, so what I can say, I am, I will complete a strength of material. I'll complete strength of material at app, an academy learning app. Okay, and I will complete manufacturing in the YouTube. So till now this is what I have planned, and based upon that I will based upon the requests, I will try to make the videos. So this is the one of the most demanding videos is there, because from vapor power cycle a lot of questions being asked in this thermodynamics. So hence we so hence I have tried my level best to get to simplify these concept and present to you, right? So I'm just presenting the simplified concept of vapor power cycle. Hope you people will like it and understand the this concept. And this is the first part. Subsequently I will be able to make the second and third part. A lot of them would be there. So this is what is from my side. Okay, so yes, good afternoon, Aditi. Good afternoon, Mukta. So so I'm going to start the vapor power cycle. So before starting the vapor power cycle, I would like to ask you, what is a thermodynamic cycle? Okay, Asis, I will try my best, because I'm not getting so much of time. But since this vapor power cycle is very much of great importance, that's why I have started this. Based upon when I will have a time, I will definitely try to make these videos. Please comment in my videos whatever the you subjects you want to study, or whatever the topics you want me to make the videos. Feel free to comment in that videos. I will try my level best to make the videos, so that it is benefit for you and for everyone who is preparing for GATE as well as ESE. Okay, so now, before starting this, I would like to ask you, foundation in thermodynamics. Okay, अदिति जी हिंदी में तो बस ठीक है मैं बोलूंगा. Aditi ji, for you I would say if at some place if you are not comfortable to understand, then please do let me know. I will definitely again tell you to make you understand, but don't worry about it, don't worry. And Subham Raj, okay, I will try I will try, Subham Raj, to make some videos to start for a foundation things, for to make a foundation in the thermodynamics, because yes, thermodynamics is one of the like basic subject for me. Basic subject is the mechanics. For me, basic subject is the thermodynamics. These things are like laying your foundation. If foundation is good, you can always go for a heat transfer. If foundation is good, you can always go for a power plant. If foundation is good, you can always go for a design, because these things are application part. Foundation is mechanics, foundation is your thermodynamics. So these things are foundation. I will definitely try to make some videos so that your foundations will get good. Okay, okay, so चलिए अब मैं स्टार्ट करता हूँ. For time being, now I will start the vapor power cycle. So before starting the vapor power cycle, I would like to ask you, what do you mean by thermodynamic cycle? Do you have any idea about thermodynamic cycle? And first and foremost thing is that मेरे प्यारे सभी दोस्तों, कृपा करके रिप्लाई किया करें. I really want a interactive session. Okay, and if the session is interactive, then I will also be happy to teach you. Okay, so just whatever wrong or right, whatever is there, just try to give the answer. So do you have any idea about thermodynamic cycle? What is thermodynamic cycle? Any closed cycle that undergoes various changes due to change of pressure, temperature. Okay, great. Any other? It will help us to deal with the application subjects such as HT and PP. Okay, yes, it is very much important. It is very much important for the application part, and hence see, vapor power cycle is the application, right? And hence I am starting this with this first terminology, thermodynamic cycle. Okay, great, great. Participation is very good. So see, what is thermodynamic cycle? See, what is thermodynamic cycle? So in a simple word, I can define the thermodynamic cycle as all those cycle or any processes in which initial as well as the final state of a system is same. Clear? See, all those process, all those cycle or process in which initial and final state of a system is same are known as thermodynamic cycle. Okay, this is what is the thermodynamic cycle. Sir, जो भी प्रोसेसेस होंगे उनका इनिशियल और फाइनल स्टेट अगर सेम हो, दैट इज कॉल्ड एज thermodynamic cycle. Clear? For example, if this is the TS plot, I have started from this point, and again I have reached to this point again. So final and initial point both is this, and hence this is a thermodynamic cycle, and hence it is a cycle. It will have some direction. Clear? So this is a basic definition of a thermodynamic cycle. Now see, why there is a need. What is a need? What is a need? Why we need a thermodynamic cycle? Why we need thermodynamic cycle? So please understand why we need thermodynamic cycle. Continuous because continuous conversion of heat from work or work from heat. So whenever whenever we require the continuous conversion of heat from work and work from heat, then in these two conditions we require thermodynamic cycle. Clear? So basically we have understood what is thermodynamic cycle. So thermodynamic cycle is that a cycle in which its initial as well as final state of a system is same. So this is the thermodynamic cycle. Now the question arises, why there is a need to of a thermodynamic cycle, and why we are going to study these things? Because sir, in application parts, in see, in the thermal power plant or in any gas power plant or any things, we want a continuous conversion of heat from work and work from heat. So only and only a thermodynamic cycle can do this, and hence we are studying the thermodynamic cycle, right? Now next most important thing is heat engine cycle. First of all, you have to understand what is heat engine cycle. What is heat engine cycle, and so what is heat engine cycle? See here, what is heat engine cycle? So like cycle or cyclic process where heat where heat is converted into work. See, this is heat engine cycle. In heat engine cycle, what we are doing, we are converting heat is converted into work. So this is the heat engine cycle. Now if I talk about heat pump or refrigerator. So can you tell me now, in this context, can you tell me what is the difference between heat engine cycle and heat pump or refrigerator? Can you tell me? Please reply me. Can you tell me what is the difference between them? See, I have told you what is a heat engine cycle. A cycle or any cyclic process in which what I am doing, sir, I am converting this heat into work. Clear? Now, what is a heat pump or refrigerator? Tell me, what is heat pump or refrigerator? Very simple, sir. Heat pump or refrigerator is what? In this work will be converted into heat. Okay. So this is the basic function of a heat pump or a refrigerator, right? Yes, Indrajit, work is done on the system and converted to heat. Yes. So this is what is the heat pump or the refrigerator, right? And see, since since heat engine since heat engine cycle produces mechanical power, hence hence they are hence they are hence they are known as power cycles. Clear or not? Reverse of heat engine. Yes, Ashish, it is reverse of heat engine. So now it is clear or not, what is a power cycle? पावर साइकिल के कॉन्सेप्ट क्लियर हुई कि नहीं सर? कि पावर साइकिल बोलते किसको है सर? हीट इंजन. आई हैव सीन दैट हीट इंजन इज व्हाट? Converting a heat into work. Heat into work, that is heat engine. Now what is heat pump? Again reverse, heat to work. Now heat pump will work to heat. Now see, heat engine cycle, whatever the heat engine cycle is what? Heat engine cycle is producing work. It is producing work. So there is work is what? Work means there is a mechanical power. Work means there is a mechanical power, and heat engine cycle producing the mechanical power, hence they are known as power cycle. Now see sir, everybody please see sir. There is some classifications which are lying in the power cycles. The power cycles are basically classified into two types. What are them, sir? Let us see. First one is vapor power cycle. Okay. And the second one is gas power cycle. Second one is gas power cycle. Clear? So first one is power cycle, and first one is the vapor power cycle, and second one is the gas power cycle. Ashish Yadav, yes, yes, yes. Yes, Ajitesh ji, heat into work is equal to heat engine. Yes, that's what we have been seeing. Now, good afternoon, Girish ji. Good afternoon. Welcome to the first class. Welcome, welcome. Now, see, sir. See, I have told you what I have told you, sir. I have told you, sir, that this is a power cycle. So power cycle is classified into two types. Power cycle is classified into two types. Now, first type I have told you, that is the vapor power cycle. And the second that I have told you, that is the gas power cycle. See, dear friends, see how I have classified the power cycle into vapor power cycle or gas power cycle. How? See, there is a thin line that you should always keep in mind. This is the classification based on the phases. So see, classification based on change of phase. Okay, what is the meaning of phase? That is, suppose if this is a liquid, liquid to gas. Okay, liquid to gas. So this is the meaning of phase change, right? So if suppose if it is solid, so solid to liquid, phase is changing. Liquid to gas, phase is changing. So here, power cycle is classified based upon the change in phase. That is the vapor power cycle and the gas power cycle. Now see, under this, the phase of component may be liquid or solid or gas, right? That means what? That means phase changes. Now see, if I am talking about the gas power cycle, what is this? Under this component will possess only gaseous state or phase. See, this is the difference. What is the difference? Here, liquid, solid or gas, these things are there. Here, gaseous phase is only there. Now see, what is the example of vapor power cycle? Example of vapor power cycle is thermal power plant. In thermal power plant, we use the vapor power cycle. So this is what is the basic introduction to the vapor power cycle, and we are going to see this vapor power cycle into little bit details, as well as we are going to see every aspects of how to increase the efficiency of vapor power cycle, Rankine cycles, and these things, as well as we will also see the significance of this subject through GATE point of view. Now, before starting these things, I would like to ask with you, how many of you know to draw the how many of you actually have the idea of liquid and vapor dome? Liquid and vapor dome of a TS diagram of these things. How many are you are comfortable in this लिक्विड वेपर डोम, टेल मी। लिक्विड वेपर डोम का जो ग्राफ होता है सर, कितने लोग आप लोग समझे हुए हैं? हाउ मेनी ऑफ यू हैव अंडरस्टूड वेरी मच क्लियरली? टेल मी। नॉट कंफर्टेबल विद द ग्राफ, ओके। शुभम जी, गैस पावर साइकिल का क्या? ऑटो साइकिल हो सकता है, ब्रेटन साइकिल हो सकता है ना? ब्रेटन साइकिल कितना बड़ा बड़ा साइकिल है। दीज थिंग्स आर देयर। सो गैस पावर साइकिल में जनरली हम लोग क्या करते हैं सर? गैस पावर साइकिल में हमारा ऑटो साइकिल होता है, ये सब साइकिल होता है, रिक्सन साइकिल होता है, एटकिंसन साइकिल्स होता है। नॉट कंफर्टेबल विद द ग्राफ, ओके। चलिए देखते हैं। if i would if I would ask with you, what is the boiling point of a water? Can you tell me? Can you tell me what is the boiling point of a water? Can you tell me what is the boiling point of a water? Tell me. Tell me boiling point of a water. Please tell me the boiling point of a water. I'm waiting for your reply. 100. Okay. Anybody else? 100, 273K, and at atmospheric pressure, boiling point of water is 100 degrees Celsius. See, Indrajit, you are very correct. You are very correct. See, all of you, when I have asked with you what is the boiling point of water, you should ask with me the very first question, sir, why you are asking with me the boiling point of water? Sir, you haven't told me about the pressure. What is the pressure? At what pressure you want the boiling point? Tell me. So you haven't asked any question. So first of all, think in mind that whenever I will ask a question with you, that tell me the boiling point of water, your first question should be with me, that tell me the pressure. Tell me the pressure, because at different and different pressure of the water, boiling point of water varies. There is no thumb rule that there is 100 degrees Celsius, right? See, 100 degrees Celsius is for the pressure. If the pressure is 1.01, see here. I'm just drawing. Let me draw it and then I will tell you. See, this is a chart. See, this is a chart. Suppose this is 100, 120.2, 133.5, 151, 36.1. See here, everybody, please see here. You can see this is a chart, steam table chart for a water. This is a steam table chart for a water. Now see, you can see if the pressure is 1.01 bar, my saturation temperature or boiling temperature is 100 degrees Celsius. Now see, when my pressure is 2 bar, temperature is different. My pressure is different, temperature is different. My pressure is increased, temperature is increased. See, when my pressure is increasing, temperature is increasing. Clear? So when my pressure is increasing, temperature is increasing. Similarly, sir, you can easily see here that when pressure is decreasing, boiling temperature decreased. Pressure is decreasing. When pressure has decreased, boiling temperature decreased. Now, see see here, if I want to make a graph with these data, if I want to make a graph with these data, see what will happen. Suppose if I want to make a graph, that is, in this temperature is plotted, in this temperature is plotted, so in this temperature is plotted, and in this entropy is plotted. Okay, in this entropy is plotted. Now see, when my pressure is 1 bar, temperature is 100 degrees Celsius. So suppose so suppose this is 100 degrees Celsius. This is 100 degrees Celsius, and this is the pressure line. This is the pressure line. This is the pressure line of this is the pressure line of 1.01 bar. Clear? So if I will plot a pressure line, this is a pressure line, and in this pressure line, what we can see here, for a 1.01 bar, temperature is 100 degrees Celsius, right? So for temperature is 100 degrees Celsius. Now see how I have drawn this. How I have drawn this. First focus in this. First focus in this part. First focus in this part. See, when when my pressure will increase, when my pressure will increase, temperature will increase. Clear? When I am increasing the pressure, temperature will increase, but at this point it will reach to a temperature of 100 degrees Celsius. Clear? It will reach to a temperature of 100 degrees Celsius, and after reaching the 100 degrees Celsius, we know that at 100 degrees Celsius water will start boiling, and after boiling, here will be phase change. Here will be phase change. Okay, so even if I'm giving the heat, okay, so suppose what I'm telling, that if I have something here, water is there, right? And in this water, if this water is, this is a piston cylinder arrangement, okay, and in this piston cylinder arrangement is there, and you are hitting this water arrangement, right? You are hitting this water arrangement from downward direction. Okay, so what will happen even if you are hitting it, even if you are giving the heat, right? Even if you are giving the heat, since it is going a phase change, hence a latent heat will be there. Latent heat will be there. Okay, so due to this phase change, this graph is flat, and after once it has been properly undergone to the vapor stage, here it is what, here it is the liquid stage, here it is at a liquid stage, right? And here it is at vapor stage. Once it has reached to the vapor, again when you are giving the heat, right? When you are giving the heat when you are giving the heat, it will increase, right? The temperature will increase, so the temperature of vapor will increase, right? So here at this point, temperature of vapor are increasing. Clearly? So clear, these things are clear to you? Now see now see if if I will plot another graph for 2 bar, if I will plot another graph for 2 bar, suppose this is the graph. Clear? Now at this graph again, I will have like this, I will have a graph like this. Clear? So this would be like, temperature would be 120 degree Celsius, 120.2 degrees Celsius. So this is the plot for 2 bar. Clear? Now again I'm plotting another graph. Again I'm plotting another graph, and that is for, suppose, for a 3 bar, right? So I will get like this. Now see what you can see from here. What you can see from here is this. Try to understand. Try to understand. When I was when I was having a 1.01 bar, right? 1.01 bar was there, and 100 degrees Celsius was the boiling temperature. At this much amount of latent heat was required. Clear? This much amount of latent heat is required. Now again, what I did, I have increased I have increased the pressure, and hence temperature of the boiling point increased. So now you can see latent heat get reduced compared to this. Latent heat get reduced. Now next is what? Next I have plotted the graph for a 3 bar, and I can see that latent heat get reduced more drastically, right? So a time will come, a time will come, a time will come at a certain point, a time will come at a certain point. At this point, what will happen? This latent heat, there is no requirement of latent heat, and automatically at that point the phase will change. Okay, so automatically there will be a point that at that point, once the component reaches to that point, phase will change. And hence if I will draw, if I will draw the locus, if I will draw the locus of these things, right? If I will draw the locus, see here, if I will draw the locus of these all points, whatever the points we have got, then I will be having a nice dome shape structure, a nice dome shape structure for water. Clear? When I will be drawing this, I will be getting a nice dome shape structure for water. So this dome shape structure of water is clear to you or not? How I have made this dome shape structure of water, this is clear to you or not? Tell me, tell me. So here at this stage, what is there? Liquid phase is there. Liquid phase is there. And here what is there, sir? Here it is vapor is there, right? And in between there, liquid plus vapor both is there. Now tell me, is this clear to you or not? Is this clear to you or not? How I have made the vapor dome structure, is this clear to you or not? Okay, great, great. It is clear to you. It is very much good. Now, if you have any doubt till now, then let me please tell me so that I can clear your doubts. Okay, okay. So you don't have any doubt. So I am proceeding to the next. Now see. Yes, 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 Subham Raj, it is correct. See here, not only temperature is increasing, Subham Raj, temperature is also increasing as well as pressure is also increasing, right? Pressure is also increasing. Okay, now we are going for design of a power plant. Design of a power plant. How I will design a power plant? So I will design a power plant with some thermodynamic design, and what is this thermodynamic design, sir? It is designed on the basis of thermodynamic criterion, okay, or we can say some thermodynamic performance criteria. Okay, now what is this, sir? What is this? See, I am drawing a little bit thing. See here. To design a thermodynamic power plant, what is the first thing that we do? We place a boiler. Okay, so there is a boiler. Firstly, try to understand, and when I will tell you that if you have any doubt, if you have any confusion or any doubt is there, then you please ask with me. I will clear every doubts. Okay, but just for time being, try to understand and try to get feel of the things. Okay, so what is the, this is their boiler, right? First we are putting the boiler here, right? And we are connecting the boiler, we are giving the heat from the boiler to the turbine. Okay, next is what? Next is this from turbine outlet, it is fed to the compressor, it is fed to the condenser, sorry, it is fed to the condenser. Now see, after the condenser, it has been fed to the condenser, it is fed to the feed pump, it is fed to the feed pump, and then it is here. I'm explaining everything. See here, see, first of all, this is my turbine, and this turbine, whole turbine is insulated. Okay, turbine is insulated, so that there is a no loss of heat is there, adiabatic condition is maintained. Clear? So this turbine is heat, this turbine is totally insulated. Now see, what is the thing? Boiler is there. What is a boiler? Boiler is a type of a container in which water is there, and the water, whatever the water is inside that, it is heated, it is heated. So we give heat to the boiler. How we give the heat to the, how we actually give the heat to the boiler? We use the coal, we use the coal fuel, we in place of a fuel we use the coal. So almost all the thermal power plants are based upon the coal based, right? They are coal based thermal power plant. So we use a coal as a fuel, we heat it, and with that heat we are heating the water present in this boiler, right? So suppose the heat that I am giving to the boiler is qb. Okay, qb, and this is at a first state, let it be at a first state. Now this heat you are giving to the boiler, this is sent to the turbine, this is sent to the turbine. Now you have fed the heat to the turbine, and this turbine will do some external work, that is work in due to turbine. Clear? Now after the work has been done by turbine, after the work has been done by the turbine, it is fed to the condenser, it is fed to the condenser, it is fed to the condenser. And in this condenser, there is a, see here, and in this condenser there is a coil, there is a small coil is there, and in this small coil actually a cooling water flows, a cooling water flows throughout it, right? A cooling water, a cooling water flows throughout it. Okay, so a cooling water flows throughout it, and heat is rejected from here, heat is rejected from here. So, and once the heat is rejected, see, turbine, after from the flowing from the turbine, it is fed to the condenser, and in the condenser that water is lower down, that heat is lowered down of that water, and hence there is a rejection of heat, there is a rejection of heat. Next is what? It is fed to the feed pump, and feed pump has the work to, we are giving the work to the feed pump, we are giving the work to the feed pump, that is the wp, and this feed pump is actually pumping the water, pumping the water to the boiler. Now see, this is the basic idea what I have given. Now I'm explaining everything in the great details. Okay, now I'm explaining everything in the great details. Now before that, let it be at a state 1, and this to be state, so this is also state 1. Clear? This is also state 1. This would be state 2, this would be also state 2, clear? This would be state 3, and this would be state 4. Okay, okay. So this would be state 4. Now see, this is the basic design of a power plant. This is the basic design of a power plant. Now see here, before going into more details, I would tell you something. I would tell you something with this graph. I would tell you something with this graph. What is happening here? What is happening here? See, here is the liquid phase. Clear? Here is a liquid phase. Here is a volume. Here is a vapor phase. Clear? Here is a vapor phase. Now see, if the this is the saturated state. This state is known as saturated state. Now, if the gaseous particle, if the vapor particle is at this state, right? That is at a vapor. If the water particle is at a vapor state, this state is known as superheated. Okay, so I think you are not. Let it be there. You're not able to see it because due to cam. See here. So this state is actually known as superheated steam. Okay, so this state is known as superheated steam. Now please tell me, what do you mean by superheated steam? What do you mean by superheated steam? What do you mean by superheated steam? Tell me. रोहित सर हीट एक्सटेंसिव प्रॉपर्टी है सर हीट क्या है सर better to say heat is actually not neither extensive property nor a intensive property. Okay, saturated steam को जब heat कर देंगे तब. Okay, see here everyone, see here. What is the meaning of superheated steam? Superheated steam is a type of steam at a temperature higher than its vaporization point. See, this is the vaporization point. See, this is the vaporization point, and if the temperature is higher than the vaporization point, clear? This is the higher than the vaporization point, and at absolute pressure, right? At absolute pressure, or at whatever the pressure you are seeing where the temperature is measured. So at that state, whatever the state is there, that is called as superheated steam. So I think superheated steam is clear to you. Now see here, at one steam enters at the high pressure turbine. See, at one boiler, from boiler, steam is entering into the high pressure turbine. So high pressure and temperature is there, high pressure and temperature, and comes out rejecting at the low pressure and temperature. Clear? See, boiler is feeding the steam at high temperature and high pressure, but after the turbine, once the turbine has done the but after the turbine has done the work, then it is being rejected, so it comes out rejecting at low pressure and temperature. Okay, now see at 2, what is at 2 happening? At 2, steam is of wet steam. See, earlier maybe, see here, these kind of things, these kind of like this is the state, saturated state or superheated state. So saturated or the superheated states are actually fed to the turbine. Okay, these are actually fed to the turbine. See here, if I plot, if I plot if I plot a vapor dome here, now I can plot a vapor dome. You don't have any problem in this. Okay, so this is my vapor dome. Okay, this is my liquid vapor dome, and here this is the temperature, this is the TS plot that what I am doing. And suppose I am having some pressure, suppose I am having some pressure, and the pressure is this is the one pressure, and this is another pressure. Okay, so there is a two pressures, there is a two pressure. Let this pressure be pressure of boiler. Clear? Pressure of boiler. And this is the, let this pressure be pressure of condenser. Now see here. So at state 2, so at state 2, what I can say that at steam, at 2, steam is of wet steam which is passed through condenser, which is passed through the condenser, where condenser extracts the latent heat, where condenser extracts the latent heat and expelled liquid of saturated state, right? So it will extract the latent heat, and hence what it will do, it will lower down the temperature of water, and hence heat will rejected, and hence heat will rejected. I will also tell you why condenser is used, what is the most significance at later stage, because once you will be prepared with the concepts, then I will tell you, and then you can relate these things. So I will tell you why. There is an interesting thing why I am using the condenser. Okay, so I will tell you at later stage. Now see, it is a steady flow energy, it is a steady flow process, hence pressure at point 2, hence pressure at point 2 is equal to pressure at point 3. So this is the most important thing, pressure at point 2 is equal to pressure at point 3. Since it is a steady flow since it is a steady flow process, so pressure at point 2 is equal to pressure at point 3. Now you will ask with me, sir, turbine is also the steady flow process, then why there is a loss in the pressure? Sir, turbine is also a steady flow process, then why there is a drop in a temperature, why there is a drop in a pressure? So see sir, the turbine and feed pump, see, the turbine and feed pump both are steady flow device, but there is a change in pressure, there is a change in pressure because there is a mechanical work. Okay, so mechanical work is extracted from turbine, mechanical work is extracted from turbine, and this mechanical work you are giving to this feed pump. Clear? So mechanical work you are extracting from the turbine, and the mechanical work you are giving to the feed pump, hence there is a change in pressure, hence there is a drop in a pressure. But see, in this boiler, in the boiler and condenser both operates at a constant pressure, both operates at a constant pressure, because these are the steady flow energy, steady flow device, hence I can say P2 is equal to P3, as well as P1 is equal to P4. So P1 is equal to P4. Now see, P1 is equal to P4 is equal to, I have considered as pressure of boiler, pressure of boiler, and P2 is equal to P3 is this is considered as pressure of condenser, pressure of condenser. Clear? Till now everything is clear to you? So what is the most important thing that we have seen here till now? What is the most important thing that we have seen here till now is that boiler and condenser operates at the constant pressure. Boiler and condenser operates at the constant pressure. Though turbine and feed pump are steady flow device, but there is a mechanical work, there is a mechanical work, and this mechanical work is extracted from the turbine, hence there is a drop in a pressure, hence there is a drop in a pressure. And see, due to the application of extra work, due to the application of this extra work, there is a rise in the pressure. See, earlier the 3 state was there, now it is reaching to the state 4, hence since you are applying the extra mechanical work, hence there is a rise in the pressure. So I think this is clear to you. Now see, now see, now see what I can say. So what is the network? What is the network? So can I say that work done by turbine minus work done by pump is the network? Right, network, because we are extracting the work from the turbine and we are giving some work to the pump. So what is the network? Difference between them, that is the network. Clear? And see, what is the net heat? What is the net heat that is getting you from here? So see, you are giving the heat, that is the QB. Okay, and this QC is rejected, and this QC is rejected, so you can say that net heat will be QB minus of QC, heat added to the boiler minus heat rejected by the condenser. So these things are clear or not? Please tell me, till now यहाँ तक कोई तकलीफ है क्या? Till now, if you have any problem, then tell me. If you have any problem, then please tell me. Tell me. Now see. Okay. Now see. This is a state 1 and this is a state 2. Clear? So this is a state 1 and this is a state 2. So state 1 is boiler. So from the boiler we are giving the steam to the टर्बाइन. सो सी, बॉयलर का टेम्परेचर सर क्या होगा, वहां पे टेम्परेचर तो बहुत ज्यादा होगा, है ना. सो फॉर अ टाइम बीइंग आई एम कंसिडरिंग दैट दिस इज the state of a boiler. This is a state of a boiler and this state is the saturated steam. Okay, so steam is saturated, and at that state this steam is fed to the turbine. Steam is fed to the turbine. See, so this stage is known as, this stage is, at this stage turbine is being heat is being fed to the turbine. Now see, there is a work done by the turbine. So turbine work is extracted here, and throughout this you are actually giving the heat. Okay, now see, this turbine work is there. Now see, after it is reaching to the turbine, after it is reaching to the turbine, see, after the turbine it is state 2. So state 2 to state 3, this water is fed to the condenser. Okay, this water is fed to the condenser. So see here, so this water will go to the condenser, and hence see, you can see that there is a rejection in temperature. There is a rejection of heat, that is QC. Let us assume that is a QC. Now see, this was a state 1, this was state 2, this will be state 3. Now see, from state 3, this is a lower pressure, and I want to get to this higher pressure. So we need a pump, and hence this feed pump will move the state 3 to state 4. Okay, so see here, so here there will be state 3 to state 4. Clear? So this is the state 3 to state 4, and this is the pressure line. Now see here, so this is the state 3 to state 4, and throughout this, see, once it has reached to the state 4, throughout this is from state 4 to state 1, heat is being added. Okay, heat is being added, and this heat which is being added is the boiler heat. It is the boiler heat. Okay, and see, this is the directions. Okay, this is the direction. So I think this graph TS plot is clear to you. Okay, so there is a work done by turbine, and and in this here you are giving the pump work. And see, everybody see here, this is actually Rankine cycle. This is nothing but Rankine cycle. So based upon this cycle, power plants are designed, and we are going to see these things in little bit great details, that how these things are very much important and how these things are changing the lives. Okay, so till now, do you have any problem? Because I have introduced the concept of Rankine cycle to you, because I have introduced the concept of ranking cycle to you. So if you have any problem, then please ask with me. If you have any problem, then please ask with me. Otherwise, I'm in. I'm proceeding. See, see, this is what we have seen. Explain once more. What I should explain once more, Subham? Tell me which ranking cycle this thing. See here, see here what is happening here. Function of condenser. See, Assis, for a time being, for a time being, see, इतना समझ लीजिए। अभी मैं कंडेंसर का बहुत अच्छा से बताऊंगा लॉजिक, लेकिन अभी नहीं बताना चाहता, क्योंकि जब थोड़ा सा आप कॉन्सेप्ट आपको समझ में आ जाएगा तब मैं उस लॉजिक को बताऊंगा, तो आप बहुत अच्छे से रिलेट कर सकते हैं। ठीक है, आधा घंटा रुक जाइए, मैं आपको ही बताता हूँ। सी हियर, बट बिफोर दैट आप अभी के लिए ये समझ सकते हैं कि टरबाइन यहाँ पर है, ये टरबाइन है। टरबाइन से क्या हुआ सर? टरबाइन से हमारा निकला स्टेट 2 पर स्टीम। ठीक है, यहां पर क्या था? यहां पे सपोज करें सैचुरेटेड स्टीम हमने फीड किया। सी हियर, आई हैव फेड द सैचुरेटेड स्टीम टू द turbine. I have fed the saturated steam to the turbine. Now see, once I have fed the saturated steam to the turbine, so here what I have found, this is the state, that liquid plus vapor state, and this is very hot. This is very hot. So see what I am doing. What I am doing, there is a condenser. There is a condenser, and from this condenser, this hot liquid plus vapor mixture is being passed. And see, I am feeding a cooling water through a coil. A cooling water through a coil. This cooling water will do what? This cooling water will extract the heat from that liquid plus vapor that is coming from the turbine, and it will reject the heat outside, and it will decrease the temperature. It will decrease the temperature. Okay, so what is the function? To reject the heat. To reject the heat. And see, uh, Subham ji, please see here. See here. See here. What is happening? From the boiler, see, from the you are feeding a saturated, you are feeding the saturated steam to the turbine. Okay, so you have fed the saturated steam to the turbine, and this turbine has done a work, that is WT. Now see, once the turbine has been once the turbine has done the work, now you are using the condenser, and the condenser is rejecting the heat. The condenser is rejecting the heat. Now it has reached to the state 3. And what is this state 3? State 3 is the lower pressure, that is pressure of the condenser, lower pressure. Now see, in order to pump this, in order to go to the state 3 to state 4, we require some external pump. So here the feed pump is used to force these liquid plus water, that is, here is a liquid, right? Here is a liquid, here is a liquid plus vapor state is there, here is a liquid. So liquid is being pumped out to the state 4 with help of a pump. So see here, that is what we have seen, right? Now see, next what is there? From state 4 to state 1. See here, what is from state 4 to state 1? State 4 to state 1. See, whatever the water you are giving to the boiler, so boiler will heat the water which has been given to the state 4 and to the state 1, right? So see, there is a continuous heating of the water is there. So there is a continuous heating of this water is there, and that is the QB, that is heat given to the boiler, heat given to the boiler, right? So I think this is clear to you. I think now graph is clear to you. Now see, now see, we are giving some heat to the boiler. Okay, so this is a state 1, and see, we this is like adiabatic is there. If you have any doubt, then tell me. This is a adiabatic thing. Adiabatic is there. Now see, this turbine is actually working. Wt is the work. Okay, Wt is the work. So Wt is the work. Now see, from condenser, a heat is being rejected. That is a QC, and this state is 2. This state is 1. This state is 3, and this state is a 4. Okay, so this is what we know. Now I'm writing the steady flow energy equation. Now I'm writing the steady flow energy equations to the for all the devices. Okay, for all devices. See here. Now when I will write the steady flow energy equation, see, this is a state 1, this is a state 2. Clear? This is a state 2, this is state 3. This is state 3, this is state 4. This is state 4, this is state 1. Now see, Viplav, I'm very fine, very fine. How are you? See, so this is the thing. So now you have to understand these things. ठीक है सर, यहां तक मैंने आपको सब कुछ बता दिया. Now our aim is to analyze the steady flow energy equation for the devices. Now see, first device what I am taking is the turbine. Okay, for a turbine, what would be the steady flow energy equation? See, here is the one state. State 1 is there, so I would consider the enthalpy 1 at state 1. Here is a state 2, so I would consider enthalpy at state 2. So for a turbine, the work would be H1 minus H2. Okay, H1 minus H2. Next thing is what? Next thing is, if I will do for a condenser, see, this is a condenser, this is a feed pump. Okay, in pump we are giving the work, that is a WP. Clear? So now if I would do for a pump, suppose for a pump, if I will do for a pump, now how can I write for a pump? See here, how can I write for a pump? If this is the WP, so this is a state 3, so this is H3. Suppose this is H3. Enthalpy associated with the state 3 is H3. Enthalpy associated with the state 4 is H4. So now see, you are giving the work. So you are giving the work. So just for example, think about it. Here you are giving the, suppose this is H3 is being fed, WP is being fed, and H4 is out. So total in, what is total in? That is WP plus H3. Total out, what is out? Out is H4. So from here I can easily say WP is equal to H4 minus H3. So this is a good handy technique. You can always do sum of in equal to out. So see, sum of in equal to out. So from here I can very easily say WP is equal to H4 minus H3. ऐसे आप क्या कर सकते हैं, ये छोटा सा चीज अगर आपके दिमाग में रहेगा ना, तो आप बहुत आसानी से ये चीजें को बना सकते हैं. ठीक है, चलिए next thing what we are going to analyze, is about the boiler. Now see, what would be the cases for a boiler? See here, for a boiler, this is a state 1. So enthalpy associated with the state 1 would be H1. Okay, now see, how can I write? So see, QB you are giving, H4 you are giving, and this is out. So QB would be H1 minus H4. Now after that there is for a condenser. How I can write for a condenser, sir? How can I write for a condenser? QC is going to be is equal to, this is a state 2. So enthalpy associated with the state 2 is H2. Enthalpy associated with the state 3 is S3. Now see, QC is outside, H2 is in, S3 is out. So in is equal to out. If you will do it, H2 minus H3. So see, these all I have written with the basis of steady flow energy equations, but I am just telling you the in equal to summation of in equal to out, so that ये बहुत हैंडी होता है, ठीक है। समेशन ऑफ इन इक्वल टू समेशन ऑफ आउट अगर हम कर देते हैं तो हम बहुत आसानी से सब चीज बना लेते हैं, बट दीज इक्वेशंस आर कमिंग फ्रॉम स्टेडी फ्लो एनर्जी इक्वेशंस, राइट। सो आई हैव रिटन everything for turbine, pump, boiler and condenser. Now see, if I would define a efficiency, so how I would define efficiency? How would I would define efficiency? So efficiency is defined as net work by heat added. Net work by heat added. Clear? So this is how the efficiency is defined. Now see. So now efficiency is net work by heat added. So what is heat added? What is net work? Net work would be work done by turbine minus work done by pump. And what is the heat added? See, this is the heat added. QB is the heat added. Clear? QB is the heat added, that what we are seeing now. So I can say QB is the heat added. Clear? Now see, what is work done by turbine? H1 minus of H2. So I am just writing here, this is H1 minus of H2. What is work done by turbine? What is work done by pump? See here, H4 minus H3. H4 minus H3. Now what is QB? What is QB? See here, QB is H1 minus of H4. H1 minus of H4. Now see, if I would interchange these things, then I will get, see, H1 minus of H4. If I will do these things like H1 minus of H4. Okay, now there is minus of H2 and plus of H3. So I'm doing as minus of H2 minus of H3 and H1 minus of H4. So if I will do this, I will get as 1 minus of H2 minus of H3 by H1 minus of H4. Okay, now see here. What is this? What is this? Can you tell me H2 minus H3 is what and H1 minus H4 is what? Tell me. What is this and what is this? Tell me. I want answer from you. What is H2 minus H3? What is H2 minus H3? Okay, I think you are not understanding these things, right? Tell me if you are not understanding, if you are having a problem. Okay, see here. Everybody, please see here. QC, yes. See here. What is QC? H2 minus S3. H2 minus S3. So I can replace this H2 minus S3 with QC. Now what is H1 minus H4? What is H1 minus H4? See here. What is H1 minus H4? QB is H1 minus H4, right? So here also I have written QB H1 minus H4. So this is QB. So my whole equation changed to 1 minus of QC by QB. And what is this QC? What is this QC and what is this QB? QC is heat rejected. And what is QB? QB is heat added. And hence from here first law is well valid. Clear? First law is well valid. So this is the things that we have seen. Now now till now, if you have any doubt, then please ask with me. If you have any doubt, then please ask with me. क्योंकि अब मैं आगे बढ़ने वाला हूँ, कोर्स में आगे बढ़ने वाला हूँ. ठीक है. Now see here. Now see here. If I talk about the pump, if I talk about the pump, see here. If I talk about the pump, so pump work is what? Pump work is H4 minus of H3. See here H4 and H3. See here H4 and H3. So see, meanwhile, if you have any doubt, then please ask me, because at in between them, if you will ask, then whole teaching will get disrupted. Okay. कोई भी दिक्कत है तो आप मुझसे पूछ लें अभी, फिर मैं नहीं देखूंगा चैट बॉक्स को. ठीक है. Okay. Okay, fine. See here 1 to 2, 1 to 2. See here 1 to 2. So 1 to 2 process is isentropic process. Okay, so 1 to 2 is isentropic process. Clear? What is the meaning of isentropic process? That is S1 is equal to S2. Entropy is same, and this is reversible. Okay. So now, if I will say that this is 1 to 2 is isentropic process. Clear? So now see, I can say that S1 is equal to S2. S1 is equal to S2. So S1 is equal to S2. But see, but say S2 is this, at S2 is this point. S2 is this point. Now, how can I write the S2? I can write the S2 as SF, that is the entropy of the fluid, of the liquid, plus X into SFG. Okay, that is also written as Sg minus Sf. I hope these things you have studied in your pure substances classes, right? You have studied these things in your pure substance classes. Okay, so I can write the S2 as S2 plus SF plus X SFG. Now see, what is H3? So this is from 1 to 2 process, from 1 to 2 process. Clear? Now see, if I would talk about the pump work, let me talk about the pump work, right? Let me talk about the pump work. So what is the pump work? So we know that WP is equal to H4 minus of H3. WP is equal to H4 minus of H3. Now see, since 3 to 4 is an isentropic process, so what I can write, see here, this equation can be written as this. This equation can be written as this. WP can be written as, this is TdS is equal to dH minus of VdP. Since 3 to 4 is isentropic process, so I can write as TdS is equal to dH minus VdP, and hence see, I can say that since it is an isentropic process, isentropic means what? Entropy is same, delta S is equal to 0, so this is going to be is equal to 0, and hence from here dH is equal to VdP. dH is equal to VdP. Clear? So I am getting a result as dH is equal to VdP, and hence I can also say that dH is equal to VdP. So integral, so see, what is dH? This is from state 3 to state 4, state 3 to state 4, so I can say that it is moving from state 3 to state 4, 3 to 4, and hence the pump work can be written as, see here, this H4, let me write it here. Okay, So this is the thing that we have got till now. So see here, what I have got as this integral of dh of 3 to 4 process is equal to integral 3 to 4 process of vdp. Okay, now see, since liquid is incompressible, right, since liquid is incompressible at very high pressure value, so at very high pressure value it can't like increase the volume, specific volume of in the considerable amount. Okay, so here what happens, sir, v3 is actually is equal to v4. Okay, therefore v3 is equal to v4. So what I can write here, as this can be written as h4 minus of h3, h4 minus of h3, and this can be written as, suppose v3 is equal to v4, so just take it this v outside and considering this as v3. Okay, considering this as v3 is equal to change in the pressure is there, right, change in the pressure is there, p4 minus of p3, p4 minus of p3. Now see what I can say, that h4 minus of h3 is there, clear, and p4 minus of p3. What is p4 and what is p3? See in this diagram, p4 P4 is, see, this is the fourth stage, and this P4 is nothing but boiler pressure. This is the third, right, this is the third. So third state is nothing but the condenser pressure. So what I can replace here as P4 as nothing but boiler pressure, boiler pressure, and P3 is nothing but condenser pressure, condenser pressure. And hence P4 is replaced by Pb and Pc. Clear? So if I would write it here, H4 minus of H3 is equal to V3 Pb minus of Pc. Clear? Now see what is pump. See here, just now we have seen here in this, Wp is equal to H4 minus of H3. Clear? Wp is equal to H4 minus of H3. So this is what? This is your H4 minus H3 is your pump work. Clear? So I can say that Wp is nothing but V3 boiler pressure minus condenser pressure. Note this equation. This equation what we have got is used. This equation will be used throughout the entire calculation of the vapor power cycle. Clear? तो सर यहां तक सारे चीज समझ में आ रहा है या नहीं आ रहा है? यहाँ तक जो चीज है, ये सब चीज समझ में आ रहा है या नहीं आ रहा है? यहाँ तक जो मैंने अभी क्वेश्चन बताया, ये यहाँ तक कोई दिक्कत, कोई प्रॉब्लम? Any problem, then please ask me. Okay, so I'm assuming that you don't have any problem. So let us move to the next part. Next, I would, sir, how V3 equal to V4? Okay, see here how V3 is equal to V4. Since liquid is incompressible, so a high pressure value can't increase the volume, or better to say a specific volume, in a considerable amount. Okay, so in a considerable amount. And hence what has been assumed that V3 is equal to V4. Clear? Now see, now see. Now we are going to see the comparison. Now we are going to see the comparison. It is a comparison of Rankine cycle with Carnot cycle. Now we are going to see the comparison of Rankine cycle with Carnot cycle. See here. If this is my TS plot. Okay, so this is my TS plot, and in this TS plot, this is my liquid vapor dome. This is my liquid vapor dome. Now see, since this is a liquid vapor dome, so see what I have seen. I have seen there is a constant pressure line. So first I will draw a constant pressure line. So there is a constant pressure line. There is a constant pressure line. Clear. Okay. So these are the two constant pressure lines that we have got. Now see, from what is a Carnot cycle? See, if I would draw a Carnot cycle will be like this. Okay, so this is the Carnot cycle. Suppose this is a 1, this is a 2, this is a 3 dash, this is a 4. Let me tell as 4, 3, and let me draw it and then I will explain it. Just give me some time. So see here, this is 1, 2, 3, 4, 1. Clear? This is my Rankine cycle. Now, if I talk about the Carnot cycle, what is my Carnot cycle? Carnot cycle is 1, 2, 3, 3 dash, and 4 dash. This is my Carnot cycle. Clear? This is my Carnot cycle. And this is my Rankine cycle. Okay. Now see here. See in the above plot, 1, 2, 3 dash, 4 dash, 1. This is your Carnot cycle. And 1, 2, 3, 4, and 1. This thing you have already seen. This is your Rankine cycle. Clear? This thing is clear to you? So in these things, what I can see that if I would calculate the efficiency of a Carnot cycle, then I can say simply that efficiency is nothing but 1 minus of this is what this is this temperature, right? This temperature is, suppose this temperature to be as a T2. Okay, and this is a temperature, this temperature, let this temperature be as a T1. Clear? So I can very easily say 1 minus of T2 by T1. I am not deriving these things. Okay, I'm not deriving these things because derivation of 1 minus T2 by T1 will take so much time, and that is not needed. Okay, जितना डिटेलिंग नीडेड है मैं उतना जरूर करूंगा. अगर आप बोलते हैं तो then I will also derive it, but that is not necessary. See here. So efficiency of a Carnot cycle, what we can say, that efficiency of Carnot cycle is 1 minus of T2 minus T1, T2 by T1. Now if you will, you will have been, so this thing is clear to you. So what we can say, that what we can say for a Carnot cycle, what we can say for a Carnot cycle, so what we can say for a Carnot cycle, that since heat addition is at maximum temperature, that is T1. Okay, because see, throughout this the heat is added. Okay, heat is added, right, and throughout this heat is rejected. So heat addition is at a maximum temperature, that is T1, and heat, see the thing, only this part, right? See, this part is the Carnot cycle. Only this part is the Carnot cycle, and in this Carnot cycle, see, throughout the Carnot cycle, the temperature is constant, and at a constant temperature, heat addition is there. Clear? In Carnot cycle, at a constant temperature, see, at a constant temperature T1, throughout the heat addition is there, right? So what I can write here as, since heat addition is at a maximum temperature, that is T1, hence Carnot cycle gives a large efficiency. Large efficiency. See, so heat addition in the Carnot cycle is throughout a maximum temperature, that is T1. But now if you will observe it very closely, see, heat addition in case of a Rankine cycle, heat addition in case of a Rankine cycle is this. Clear? Heat addition in case of a Rankine cycle is this, right? So what I can say, what is the conclusion that we have got? See, but for a Rankine cycle, partial heat addition is at lower temperature, and partial is at higher temperature. Okay, so this is the most important conclusion, that what we are getting, that for a Rankine cycle, partial heat addition is at a lower temperature, right? So see, partial heat addition is at a lower temperature, and see here, partial heat addition is at a higher temperature. Okay, so what I can say, what should be the conclusion? Conclusion is temperature is varying during heat addition. Okay, so this is a case of a Rankine cycle, and this is for a Carnot cycle. Clear? This thing is clear to you or not? Tell me. This thing is clear to you or not? Tell me. This thing is clear to you or not? Tell me. Please tell me. Partial at higher temperature means what? See here. See, suppose this temperature, suppose this temperature as any value. See, this temperature throughout this. How can I do this? Okay, sorry. So like see what was happening earlier that, okay, let me draw a fresh diagram. Let me draw a fresh diagram. See here, this is my pressure, this is another pressure, and suppose from here this, this, and this. See here, see here. Suppose this as a temperature T2 and this as a temperature T1. Clear? Now this is a temperature T2. So I can say that this is the temperature T2. But what about this? What about this? This throughout this also I am, throughout this also heat addition is there. So what about these things? What about these things? Here temperature is less. Here temperature is less compared to T2, right? So that's what I have written here, that for a Rankine cycle partial heat addition is at lower temperature, so these things are at lower temperature, and partial is at higher temperature, so these things are at a higher temperature. Clear? Now see here, now see here, if somehow if this is a S plot, if somehow I consider these things, right, these things as a Tm, let us assume a Tm, that is mean temperature of heat addition. So there is a concept of mean temperature of heat addition, and what is this concept tells us that, suppose, see, we can easily say that Carnot efficiency is what, 1 minus of T2 by T1, very easily, very easily we can say 1 minus of T2 by T1, but we cannot say these things because heat addition is not as a constant temperature. So I am assuming a constant temperature, that is a mean temperature, that is Tm. This thing is being assumed by us, and this is mean temperature of heat addition, and considering this thing I am writing that Rankine cycle efficiency would be 1 minus of T2 by Tm. Okay, 1 minus T2 by Tm. Now, now now there is a one more most important thing is coming into your way, is the actual power cycle, or better to say actual vapor power cycle. Actual vapor power cycle. What is actual vapor power cycle? See, I have drawn that like this. I've drawn the graph like this, that here is the S entropy, here is the temperature T, and here is a vapor dome. Okay, and I have drawn the graphs, I have given like this. This is the pressure line, This is another pressure line. And see, suppose at this condition it is at a it is at a superheated state. So if it is at a superheated state, this would be my configuration. So let it be 1, 2, 3, and 4. Now see, everybody, please see here. What is the thing that we encounter here? 1 to 2 is the isentropic process, right? 1 to 2 is the isentropic process. But see, in actual case, 1 to 2 and 3 to 4 process are irreversible. Okay, 1 to 2 and 3 to 4 processes irreversible in nature, that are not reversible, and hence what happens in reality? In reality, 1 to 2 will process looks like this. 1 to 2 process looks like this. 1 to 2 process looks like this. Okay, so somewhat here, so that is actually known as 2 dash. Clear? 2 dash. Now 3 to 4 process looks like this. So this is 4 dash. This is 4 dash. Now see, there is a logic why these are happening this like this. See, any irreversible process, in any process, entropy will increase. If the process is irreversible, entropy will increase. Now see the entropy at point 2 and point 2 dash. Entropy at point 2 dash is increasing, right? Definitely I can say that S2 dash is greater than S2, and S4 dash is greater than S4. So from here what I can say, that irreversible process, if it is an irreversible process, entropy increases, and hence this is the actual figure. So in actual case, 1 to 2 and 3 to 4 processes are irreversible, and hence 1 2 dash, 1 2 dash, and 3 4 dash are actual. These are actual. Okay, one point will be, आशीष, see, it is not mandatory. See, आशीष जी, क्या मैं बोल रहा हूं, देखिए, जरूरी नहीं है, जरूरी नहीं है, मैं अगर एक्सपेंशन करूं, मैं यहां से भी एक्सपेंशन कर सकता हूं, क्या दिक्कत है? देखिए, डिफरेंस क्या होता है मैं समझाता हूं. If I am expanding from this point, from this one point, state of the steam is what? State of the steam is saturated. Saturated, so better to say as dry saturated steam is there. Dry saturated steam is there. But if I will take the steam at here, the state is what? Superheated. Superheated steam. Superheated steam. And I can take any steam, right? anything. So see, ड्राई सैचुरेटेड जो स्टीम है ना, वो हम नहीं डालते हैं. क्यों? अगर ड्राई सैचुरेटेड स्टीम डाले, सो वो इसमें देखिए, सी द थिंग्स, देन यू विल अंडरस्टैंड. आई विल एक्सप्लेन दीज थिंग्स लिटिल बाय लिटिल. तो हम क्या कर सकते हैं ना, सुपर हीटेड स्टीम भी डाल सकते हैं, सैचुरेटेड स्टीम भी डाल सकते हैं. ठीक है, तो ये हो गया सैचुरेटेड स्टीम. मैं अच्छी तरह से बता रहा हूं, थोड़ा टाइम दे. So this is at a saturated state. Now I can also do like this, है ना. मैं यहां से भी एक्सपेंड कर सकता था, मैं यहां से भी एक्सपेंड कर सकता था, कोई प्रॉब्लम नहीं. आई कैन डू इट. क्लियर? now see so if I would talk about the, so now work done by turbine. Now what will be the work done by turbine? See, earlier, so better to say as this is the arrow. Okay, so in this way the process is happening. So what is the work done by turbine in new case? So work done by turbine would be H1 minus of H2 dash. Okay, and what was the work ideal? What was the work ideal that we have seen? H1 minus of H2. H1 minus of H2. And since H2 dash is greater than H2, therefore work done by turbine is always greater than ideal work. Okay, so if I would talk about the isentropic efficiency of the turbine, I will be getting as H1 minus of H2 dash by H1 minus of H2. Clear? So this is your actual work, and this is your ideal work. Okay. Now, similarly, if I would talk about these things, right? This was for the pump work, right? This was the pump work. This was the turbine work, and here we are giving the pump work. So now we have talked about the turbine isentropic turbine efficiency. Now, what would be the case of a pump? What would be the case of a pump? So see, H3 and H4, H3 and H4 dash. So I can say that actual work feed work will be what? H4 dash minus of H3. See, I am writing here. So work done by pump would be H4 dash minus of H3, and work done by pump, which is ideal, that would be H4 minus of H3. This thing is clear to you or not? This thing is clear to you or not? So what I can write at the next slide, I'm writing here. So see here. So I can write as work done by pump is nothing but H4 dash minus of S3. See here, H4 dash minus of S3. Clear? Now work done by the pump, which is ideal. Okay, ideal. In ideal case, that would be H4 minus of S3. So therefore, isentropic efficiency for pump this is going to be is equal to H4 minus of H3 by H4 dash minus of S3. So this is the two things that you should remember. This is for a pump and this is for a for a turbine. Okay, clear? These two things you should always keep in mind while solving the problem. So till now, do you have any problem? Till now, do you have any problem in how I have written the isentropic efficiencies of the pump and the turbine and these things? Till now, do you have any problem? Tell me. So till now, do you have any problem? Tell me. Should I proceed? Okay, so I'm proceeding. See here. Now, 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 what is the thing that we should focus on? How we can increase efficiency of a Rankine cycle. Okay, so how we can increase the efficiency of a Rankine cycle? So see, we have seen that efficiency of a Rankine cycle is equal to what? 1 minus of T2 by Tm, where this Tm is what? Mean temperature of heat addition. mean temperature of heat addition. So first way, so first way, so first way, how we can increase the efficiency? So we can increase the efficiency by increasing mean temperature of heat addition. By increasing mean temperature of heat addition. And what is the second thing that we can do? We can, by decreasing the temperature of heat rejection. Okay, so see here, so either I can decrease this or I can increase this. Okay, either I can decrease this or I can increase this. So in both of the cases, my efficiency will increase. My efficiency will increase. Clear? Now see, let us say a new important case, that is by increasing mean temperature of heat addition. So see here, so this is a Vapour dome. PS plot is there. Now see, now see, if I have a Rankine cycle like this, okay, so suppose I have a Rankine cycle like this, okay, so this is at a some pressure P is there. I don't know about this pressure. So after that, like this, like this. Okay, now see here. Now see here. मीन टेम्परेचर तो हम बॉयलर टेम्परेचर से ज्यादा नहीं कर सकते हैं ना. मीन टेम्परेचर क्या होता है? मैं जस्ट एक कॉन्सेप्ट मान लिया हूं मीन टेम्परेचर का, ताकि मेरा ईज हो इन इफिशिएंसी कैलकुलेशंस में. ठीक है, इफिशिएंसी कैलकुलेशंस में मेरा ईज हो, इसलिए मैं मीन टेम्परेचर ऑफ हीट एडिशन को मान लिया हूं. ठीक है, एंड दैट मीन, जब मीन हो जाएगा तो ज्यादा कैसे हो सकता है? कभी भी ज्यादा नहीं होगा ना. दैट विल बी एवरेज, कहीं बीच का होगा. ठीक है, नाउ सी, नाउ सी हियर. See, we can't increase, most important thing that I want to tell you, we can't increase the temperature of heat addition according to our wish. Okay, we can't increase the temperature of heat addition according to our wish. It is also increased up to nearly about 500 to 700 degrees Celsius. For example, see here, my maximum temperature will always be fixed. My maximum temperature will always be fixed. ओके, सो इट इज नॉट लाइक दैट मैं टेम्परेचर 1000, 1200, 1500 कुछ भी कर सकता हूं. नहीं, आई कैन नॉट डू दैट. सो इन द केस ऑफ रैंकिन साइकिल, माई मैक्सिमम टेम्परेचर इज फिक्स्ड. व्हाई माई मैक्सिमम टेम्परेचर इज फिक्स्ड? बिकॉज we can't increase the temperature of heat addition. We can't increase the temperature of heat addition according to our wish. Like I think that it should be 800 or it should be 1200. No, I cannot do like that. So it is also increased up to nearly about like 500 to 700 degrees Celsius. And why this is there? Because the most important reason is that the blades of the turbine may get damaged at higher temperature and not properly work सो इफ दैट इज द कंडीशन, अगर मैं टेम्परेचर बहुत ज्यादा बढ़ा दूं तो क्या होगा, ब्लेड जो होगा ना टरबाइन का वो डैमेज हो जाएगा. इफ दैट इज द कंडीशन, ब्लेड ऑफ द टरबाइन विल डैमेज एंड इट विल नॉट फंक्शन वेल. It will not function well. So maximum temperature is fixed. So maximum temperature is fixed. Now if we increase the boiler pressure, suppose if I increase the boiler pressure, suppose if this is my next boiler pressure, if I increase the boiler pressure, okay, if I increase the boiler pressure, suppose if I'm increasing the boiler pressure, this is the boiler pressure, so again I'm increasing the boiler pressure. These are all the boiler pressure. Okay, so see, so if we increase the boiler pressure, then mean temperature corresponding to the consecutive higher pressure will increase. See here, suppose earlier, let us assume this, let us assume like this. Okay, so let us assume like this. Now see, if I would, now see, if I would, if this is my maximum temperature, so what I have understood, that during this my maximum temperature is fixed, my maximum temperature is fixed, so this line is fixed. Now if I will increase, suppose this is my pressure, suppose this is the P1 pressure, P2 pressure, P3 pressure, different pressures are there, or better to say as boiler pressure, these all are boiler pressure, so I can write as PB1, PB2, PB3. Okay, boiler pressures are there. Now see, if I would expand this, if I would expand this at some pressure, okay, suppose this is the pressure, condenser pressure, PC. Okay, so if I would expand it, then see what is the thing that I'm getting. See here. So earlier I was having this much amount of pressure, I was having this much amount of pressure, and I am expanding till this, right? Now earlier mean temperature of heat addition is what? See here. So earlier see, if I want to find a mean temperature of heat addition, I have to see this only. Okay, I have to see this only, right? From here I am getting the mean temperature of heat addition. But see, when I have increased the boiler pressure, right? Suppose this is a 5 megapascal and this is 10 megapascal, right? So when I have increased the boiler pressure, what is happening? See here, when I have increased the boiler pressure, then I am getting like this. Okay, then I am getting like this. So see, if this is, let me name it, this is 1, 2, 3, 4. Okay, now this should be 1, 2 dash, 3, 4 dash. Clear? Now see, and let this be 1 dash. Okay, now see here, mean temperature of heat addition for this graph, like 1, 2, 3, 4, right? 1, 2, 3, 4 has the mean temperature of heat addition as Tm1. Let us assume Tm1. Now for a 1, 2 dash, 3, 4 dash, for this graph I am having some different mean temperature of heat addition. This is my different mean temperature of heat addition, and this Tm2 is greater than Tm1. Okay, so see, if I am increasing the pressure, if I am increasing the pressure, then mean temperature of heat addition is increasing. Mean temperature of heat addition is increasing. Now again suppose if I have increased this pressure, again I am getting the this kind of thing. So again I will have more heat temperature of heat addition. Suppose this is mean temperature of heat addition, like this is more. Suppose this mean temperature of heat addition, this is more. But what you can see here from this figure, what you can see here is this. Observe very closely that at this point, and at this point, can you tell me at point 2, 2 dash and 2 double dash, at these 3 points, which point will have maximum dryness fraction and which point will have low dryness fraction? Or better to say, which point will have more moisture content? Tell me, from 2 dash and 2 double dash, from these 3 points, can you tell me which point will have more moisture content? Can you tell me? Okay, no problem. See here in this figure, what we can see, it is clearly, see here, it is in this figure, it is clearly visible that we get a maximum. See, if mean temperature of heat addition will be more, mean temperature of heat addition will be more at point 2. Okay, see here. So we are knowing that if we are increasing the mean temperature of heat addition, then efficiency will increase. Now see, what I am seeing here, that mean temperature of heat addition is more in this case, right? Is more in this case. But mean temperature of heat addition is more in this case, hence I am getting the efficiency in this case more, right? I am getting the more efficiency in this case. But again same, see this 2 double dash has less dryness fraction, right? So what I can say here, that from the figure it is clearly visible that we will get maximum efficiency from a Rankine cycle, with a sacrifice in dryness fraction, right? See, dryness fraction is very bad, very less in case of 2 double dash, but dryness fraction is more in case of a 2. So 2 double dash has a less dryness fraction. It simply means that at 2 double dash point, moisture content will be more. And see here, if moisture content will be more, then if moisture will be more, then what will be happening? Blade material suffers tremendous erosion due to water content or particles, okay, whatever is there. Now see, if that is the condition, there is also a condition of corrosion, right? So corrosion occurs. Okay, so these are the problem. So what I can conclude from this is that, so there is a restriction in maximum temperature and restriction in dryness fraction. See here, टेम्परेचर में मैक्सिमम, टेम्परेचर में रिस्ट्रिक्शन क्या था कि टेम्परेचर हम ज्यादा नहीं बढ़ा सकते. क्यों ज्यादा नहीं बढ़ा सकते? बिकॉज द ब्लेड्स ऑफ टर्बाइन्स में गेट डैमेज एट हायर टेम्परेचर एंड नॉट प्रॉपरली वर्क. सो माई मैक्सिमम टेम्परेचर इज फिक्स्ड. नाउ if my maximum temperature is fixed, so I cannot do anything with that. But what I did, I tried to increase the mean temperature of heat addition. So to get a mean temperature of heat addition more, I have done like pressure increased. I have increased the pressure. So I am increasing the pressure, but for that mean temperature of heat addition is less. Increasing the temperature, increasing the pressure. See here, pressure is increased. I am increasing the pressure. So when I am increasing the pressure, I am getting the more mean temperature of heat addition. But more temperature of heat addition, less is the dryness fraction. Less is the dryness fraction. And hence with this sacrifice, I can say there is a restriction in maximum temperature and a restriction in the dryness fraction. Okay, so there is a restriction in both of them. Okay, dryness fraction of component throughout expansion. This thing is clear or not? Because at another three there are contains liquid and vapors, but liquid content should not be more than 12%. See, approximate. See, dryness fraction. Let me write it here. Dryness fraction in a steam power plant should not be less than 0.85. Okay, this is the thumb rule. It should not be less than that. Okay. So this is the case. Now I think this is clear to you. Now this is clear to you. This is clear to you. Now see here. Efficiency is equal to 1 minus of T2 by Tm. Okay, 1 minus of T2 by Tm. Now when I am using the condenser, see here, when I am using the condenser, so what is happening with the condenser? Condenser makes the condensation process below the atmospheric pressure, and hence temperature of heat rejection decreases. See, what is the temperature of heat rejection? This is the temperature of heat rejection, right? See, this is the temperature of heat rejection. This is the temperature of heat rejection, right? And see, my goal was what? My goal was either I can increase the mean temperature of heat addition, or I can decrease the mean temperature, or I can decrease the heat rejection temperature. And see, condenser कंडेंसर क्या करता है सर? कंडेंसेशन प्रोसेस को बिलो एटमॉस्फेरिक प्रेशर कर देता है, जिसके कारण टेम्परेचर ऑफ हीट रिजेक्शन डिक्रीजेस, एंड हेंस एफिशिएंसी इंक्रीज. ठीक है, एफिशिएंसी अगर 1 माइनस T2 बाई T1 होता है ना, अगर T2 आप डिक्रीज कर रहे हो, इसका मतलब क्या? एफिशिएंसी इज गोइंग टू इंक्रीज. And see, this is why we use the condenser. Condenser हम क्यों use करते हैं? This is why I use the condenser. So this is very much important and like interesting thing, right? Very much interesting thing. So I hope why I use condenser, how I can increase the Rankine cycles, these things are there. See, you can control up to some limit, like that. When you are, see, suppose in the condenser you are giving the coil, right? Cooling water is there. Cooling water is automatically flowing is there, right? तो cooling water जो flow कर रहा है, तो you can control up to certain limit. You can control up to certain limit. So till now everything is clear to you. Till now everything is clear to you. Should I proceed to the next topic? Okay. See here. So now what we have understood, till now what we have understood from the above scenario, it is very clear that temperature as well as boiler pressure. See here, the temperature. See here, from the above scenario, we can easily say that this temperature as well as this boiler pressure, right? I cannot increase boiler pressure up to any limit. मैं कुछ भी बॉयलर प्रेशर भी नहीं रख सकता हूं. क्यों? बॉयलर प्रेशर अगर कुछ भी रख दिया तो यहां पर क्या होगा? ड्राइनेस फ्रैक्शन डिक्रीज करेगा. तो देर इज अ restriction in the boiler pressure. I cannot give any boiler pressure and I cannot take any maximum temperature also. So from above scenario it is very clear that temperature as well as the pressure and as well as the boiler pressure are fixed to a certain value. As above stated earlier, 85% of the minimum dryness fraction should be there, right? 85% of the minimum dryness fraction is actually acceptable. So now the question arises, if everything is fixed, then how can I increase the efficiency? How can I increase the efficiency of a steam power plant, right? So how can I increase the efficiency of a steam power plant? So the thing is that yes, it is possible to increase the boiler pressure without sacrificing the dryness fraction. See, it is how I can firstly understand by graph, and then I will explain these things. See, see here. So I know that my maximum temperature is fixed. Clear? So I know that my maximum temperature T max is fixed. Clear? As well as I also know that suppose this is the boiler pressure, right? Suppose this is the boiler pressure that is fixed. So this is also fixed. This is also fixed. Now, suppose like this. Suppose like this. This is the boiler pressure and this is fixed. Okay. So and here is a condenser. Condenser pressure is there. Okay. तो हमने अभी तक क्या देखा? Till now what we have seen that maximum temperature is going to be fixed as well as pressure, boiler pressure is also fixed, right? Because there is a restriction. अपने मन का अगर मैं बॉयलर प्रेशर ले लूं तो क्या होगा? ड्राइनेस फ्रैक्शन में कमी होगा. ड्राइनेस फ्रैक्शन में कमी होगा तो मॉइस्चर कंटेंट ज्यादा होगा. मॉइस्चर कंटेंट ज्यादा होगा तो इरोजन होगा, कोरोजन होगा, ब्लेड मेटल खराब हो जाएगा. तो ये एक्सेप्टेबल नहीं है. तो मेरा मैक्सिमम टेम्परेचर इज ऑल्सो फिक्स्ड एंड द बॉयलर प्रेशर इज ऑल्सो फिक्स्ड. सो नाउ व्हाट कैन आई डू? So this is the one of the process that we can do. We will expand this. We will expand this till a intermediate pressure. Okay, we will expand this turbine. Expansion process जो होगा सर, मैं एक intermediate process, मैं एक intermediate pressure तक करता हूँ. Clear? See here. See here, what I am doing, what I am doing. So suppose this is the P1, suppose this is a 1, this is a P1 pressure, this is a P1 pressure is there, and see what I am doing, मैं एक इंटरमीडिएट प्रेशर पर ला करके यहां पर रोक देता हूं, ठीक है। फिर से इंटरमीडिएट प्रेशर पर आने के बाद I will expand it till again the maximum temperature. Okay, I will expand it till maximum temperature, and again after expanding it, I will do this like this, right? तो अगर मैं ऐसा करूं ना, तो फिर मुझे क्या मिलता है, मेरा प्रेशर भी बढ़ता है। सी, my pressure is also increasing, as well as there is no loss in dryness fraction. See, we will heat the component. See here, let me draw it. Now understand, again I am explaining it. See, we will heat the component at the maximum boiler pressure. Okay, so we will heat the component at the maximum boiler pressure. Okay, so at the maximum boiler pressure we will heat the component and expand it till a intermediate pressure, right? So let it be intermediate pressure. So I will expand it till the intermediate pressure line, right? Now see, after reaching the intermediate, constant pressure reheating would be there. Again I would reheat this. I would reheat, constant pressure reheating would be there. Okay, and constant pressure reheating is done to such a pressure corresponding to which dryness fraction is low, or dryness fraction is supposed as 0.85. Clear? So in this way I am trying to increase the efficiency. ठीक है, ये एक तरीका जो है, this तरीका is known as reheat. This process is known as reheat. What I am doing, I am reheating these things. I am reheating the component. ठीक है, मैं 2 बार हीट कर रहा हूं, ठीक है। Now corresponding to that, what would happen? From here I will get the turbine work, right? And from here also I will get another turbine work. Clear? So these things are clear to you. And see, so let me draw these things so that you will get a good insight. So suppose there is a boiler. Okay, so suppose there is a boiler, and in this boiler, right, what you are doing, not draw this, let me draw this. Suppose this is a boiler. Okay, and from this boiler you are sending the steam to a high pressure turbine. See here, this is the high pressure. This pressure line is so see, this is P1 and this is P2. So this is known to us that P1 is greater than P2. So P1 is greater than P2 means what? P1 is high pressure. So high pressure can be handled by high pressure turbine, and P2 is a lower temperature. So I can say that P2 is at a lower temperature, that is intermediate pressure will be there. So low pressure turbine can handle this. Hence see here, so this is fed to a high pressure turbine. So this is fed to the high pressure turbine. Okay, now there is a same shaft would be there, and this same shaft is connected with the low pressure turbine. The same shaft is connected with the low pressure turbine. And through this low pressure turbine, okay, now see what is happening. From boiler, that is at state 1. सो पहला क्या होगा, हाई प्रेशर टरबाइन में चला जाता है, ठीक है। जैसे ही हाई प्रेशर टरबाइन में चला गया, फिर क्या हुआ, उसको मैं रीहीट किया, ठीक है, रीहीट किया लो प्रेशर टरबाइन तक, ठीक है, रीहीट किया लो प्रेशर टरबाइन तक। तो जैसे ही यहाँ पे देखिए ये हाई प्रेशर टरबाइन तक गया, हाई प्रेशर टरबाइन में जाने के बाद मैंने फिर से क्या किया, फिर से रीहीट किया, ठीक है, रीहीट किया। तो रीहीट कैसे करेंगे, तो एक रीहीटर होता है, ठीक है, यहाँ पर इस पूरे जगह पर आपने रीहीट किया। तो रीहीट कैसे करेंगे हम, रीहीट कैसे करेंगे हम, तो यहाँ पर देखिए कि जैसे ही हाई प्रेशर टरबाइन से मेरा निकला, तो वो जो भी निकल रहा है स्टीम, आई एम फीडिंग दैट स्टीम टू अ रीहीटर, to a reheater, okay, to a reheater. And suppose this arrangement is in the boiler, clear, suppose this arrangement is in the boiler. So what I am doing, this is the reheater, okay. So let me draw very nicely. There is reheater is there, okay, this reheater is from here. So see, earlier high pressure turbine is there. So let me first write these things. So suppose this is as a point 1, this is as a point 2, this is as a point 3, this is as a point 4, this is as a point 5, and this is as a point 6. Clear? Now see, 1 to 2, 1 to 2. So this is state 1 and this is state 2. Clear? Now see, from 2 to 3, from 2 to 3, from 2 to 3 क्या हो रहा है सर, again heating is there, right? From 2 to 3 again heating is there. So what I am doing, I am taking the steam from high pressure turbine, and this is state 2, and this state 2 steam is heated, and after heating it is at state 3, after heating it is at a state 3. So this is a reheater, this is reheater, and the function of reheater is to reheat the material, reheat the material. Fine. Now see, this is the 3, this is the 3 part, 3 point is there. Now from here again this material is fed to the low pressure turbine, see here, ठीक है, यहां से फिर से मैं लो प्रेशर टरबाइन में दे दिया. नाउ आफ्टर इट इज रीचिंग टू द लो प्रेशर टरबाइन, अगेन दिस इज expanded. So this is state 3, this is state 4, right? 3 to 4, see here, 3 to 4, 3 to 4, 3 to 4 is this, right? Now once it is reaching to the 3 to 4 state, again I am using my condenser, I'm using the condenser, and in this condenser cooling would be there. So this is the condenser, and in this condenser what is there, so from this condenser feed pump is connected, feed pump is connected, and this feed pump is fed work power pump. So pump work is given to it, and then it is, this pump work will give the, pump the water to the boiler state, right? So this is 3, this is state, this is going to be 4, this state is going to 5, and this state would be 6. Now this reheat concept समझ में आया, ये रीहीट कॉन्सेप्ट थोड़ा सा अलग है, अभी तक आपने जितना भी चीज पढ़ा है रीहीट कॉन्सेप्ट थोड़ा सा अलग है. ये चीज समझ में आया या नहीं आया, या प्रॉब्लम है, ये चीज समझ में आया या नहीं आया. दिस वुड बी योर QB, राइट, QB, that is the heat given in the boiler, okay. This would be like P2 pressure, I have already told you, this is the P2 pressure, this is the P1 pressure, and this is the, this pressure is condenser pressure, clear, this pressure is condenser pressure. सो आई थिंक रीहीट क्या होता है, रीहीट में करते क्या है, ये सारा चीज आपको समझ में आ गया होगा या नहीं आया, ठीक है, बता दे मुझे फटाफट, रीहीट इज क्लियर टू यू और नॉट. नाउ सी, नाउ सी, what is the Q added? What is the Q added? कितना हीट हमने ऐड किया है? How much heat I have added? Can you tell me? See here. What is the heat added? See, this much amount of heat is being added. First thing. Second thing is what? Second thing is what? This much amount of heat is being added. Clear? So this is the heat added. Heat added to the system is these two things. So what I can write here is heat added. What is the heat added? Heat added would be H1 minus of H6. H1 minus of H6. Enthalpy at state 1 is more than enthalpy at state 6. So H1 minus of H6. Now I have to add this also. So there would be, next would be H3 minus of H2. H3 minus of H2. Yes, Asis, where we have to do this. So this is the Q added. Next is what? Next is heat rejected. What is heat rejected? See, this is the heat rejected. This is the heat rejected. These things we have seen. This is the heat rejected. So this is let be the QC. So what I can say is H4 and H5 is there. So I can say that heat rejected would be H4 minus of H5. Clear? Now what is the turbine work? So here we have seen work T1 is there and work T2 would be there. Right? यहाँ पर दो तरीके का वर्क हो रहा है. That is see here, this WT1 is there and WT2 is there. So ये दो तरीके का वर्क जो है यहाँ पर हो रहा है. ठीक है, ये दो तरीके का वर्क जो है यहाँ पर हो रहा है. तो what I can write here, what I can write here is work done by turbine. Work done by turbine. So what is the work done by turbine? Work done by turbine is this 1 and 2. So from 1 and 2 work is being there, right? Work is being done by turbine. So this is H1 minus of H2. Clear? This much amount is H1 minus of H2. Now see, at this stage also work done by turbine is there. So this is third state and this is fourth state. So I'm going to add this as third state minus fourth state. So this is the work done by turbine. So till now, if you have any question, ask me. ठीक है, पूछ लीजिए मुझसे. अगर कोई भी दिक्कत हो तो पूछ सकते हैं बेझिझक. ठीक है. So now, if I would talk about, see here, in earlier scenario, what we have seen, that efficiency of a Rankine cycle is nothing but 1 minus of heat rejected by heat added. Clear? 1 minus of heat rejected by heat added. Now see, what is heat rejected and what is heat added? In this case, heat rejected and heat added. Heat rejected is this, heat added is this. So I can write as efficiency would be 1 minus of Q rejected by Q added, which is nothing but 1 minus of Q rejected is what? H4 minus of H5 by heat added is what? H1 minus of H6 कॉन्सेप्ट. तो नेक्स्ट सेशन मैं लूंगा जिसमें मैं आपको रीजनरेशन का कॉन्सेप्ट बता दूंगा. ठीक है, और रीजनरेशन का कॉन्सेप्ट बता दूंगा और फिर कुछ न्यूमेरिकल्स करेंगे, या फिर मैं अभी ही बता दूं रीजनरेशन का कॉन्सेप्ट. टेल मी, जैसा बोलेंगे वैसा कर दूंगा. Till now everything is clear to you? And tell me. ठीक है, चलिए मैं बता ही देता हूँ व्हाट इज देयर नेक्स्ट क्लास। ठीक है, कोई बात नहीं है, मैं नेक्स्ट क्लास लूंगा, मैं नेक्स्ट क्लास लूंगा, मैं पार्ट 2 एक लूंगा, ठीक है। टिल नाउ अभी तक आप, मैं जितना भी कॉन्सेप्ट बताया हूँ, बहुत कुछ बता दिया हूँ आज के दिन में। प्लीज ट्राई टू अंडरस्टैंड एंड डाइजेस्ट दीज थिंग्स, राइट? Please try to understand. See, I have started the lecture with the basic concept, right? With the very basic concept of thermodynamic cycle and the thermodynamic cycle. And see, from this basic thermodynamic cycle, I have started your base. I have worked on your base, and see, I have again tried to introduce the concept, then this how you are getting the vapor dome, design of power plant, then ranking cycle, and related to that how you can find the efficiency, and pump work would be there. So then we have comparison, then we have did the comparison with the ranking cycle and the Carnot cycle. And see, always this thing that we have seen, that Carnot efficiency will always be greater than ranking efficiency. Next thing is what? Temperature is less. These things we have seen. Next, mean temperature of heat addition concepts we have seen. Actual vapor power cycle. What is the actual vapor power cycle? What is in actual case? What is happening? And the isentropic efficiency related to that. These things we have seen, as well as uh, isentropic pump efficiency. These things we have seen. After that we have introduced the concept that okay, so how we can increase the efficiency of a ranking cycle का efficiency कैसे बढ़ा सकते हैं. Then we have seen that there are two methods to increase the efficiency of a ranking cycle, that by increasing the mean temperature of heat addition, right? See, we can increase this, or either we can decrease this. So by decreasing the mean temperature of heat rejection, so we can do like this. And we have already know that why we are using the condenser, what is the use of this condenser. Okay, next thing that we have seen कि सर जब मैं बॉयलर प्रेशर बढ़ा रहा हूं तो प्रॉब्लम मेरे साथ क्या आ रहा है कि यहाँ पर जो आपका ड्राइनेस फ्रैक्शन है वो कम हो जा रहा है. ठीक है, सो ड्राइनेस फ्रैक्शन इज गेटिंग वेरी मच लेस, एंड इफ ड्राइनेस फ्रैक्शन विल बी लेस, then there is a blade material will suffer tremendous erosions and corrosion will occur. And see, already we have fixed this maximum temperature. Why we have fixed maximum temperature? Because blades of the turbine at that maximum temperature will get damaged. Okay, now see, so based upon that, we have found a method that is called as reheat, and this with reheat method, I am getting the good efficiency. So the reheat is a method in which I am increasing the efficiency. Next method is also that is called as regeneration, and this method we are going to do in the next part. Asis, I will do the next part, but I am not sure when I will do. मैं करूंगा, बिल्कुल करूंगा नेक्स्ट पार्ट, बट जल्दी ही करने वाला हूँ. नेक्स्ट पार्ट भी मैं जल्दी ही डालूंगा, ठीक है. एंड इन दैट नेक्स्ट पार्ट आई विल टेल यू अबाउट द कॉन्सेप्ट ऑफ रीजनरेशंस, हीटर को मैं कैसे लगाता हूँ, कैसे रीजनरेशन होता है, एंड आफ्टर दैट how this regeneration, let me tell you, the questions are asked from reheat and from regeneration. This is the only two topics from where in this vapor power cycle बहुत क्वेश्चन पूछता है, बहुत क्वेश्चन पूछता है. सो आई हैव ऑलरेडी टोल्ड यू द कॉन्सेप्ट ऑफ रीहीट. रीजनरेशन भी बता दूंगा, उसके साथ ढेर सारा न्यूमेरिकल करेंगे प्रीवियस ईयर गेट का, और पता करेंगे कि हाउ दीज थिंग्स आर एप्लीकेबल विद द गेट. एंड बिलीव मी दिस इज वेरी इजी टॉपिक, एंड यू आर गोइंग टू स्कोर वेरी गुड मार्क्स. 4 से 5 मार्क्स पूछता है, सारा का सारा अटेम्प्ट करके रखना है, ठीक है. तो चलिए, आई थिंक यू डोंट हैव एनी डाउट टिल नाउ. So, so thank you so much for your active participation, and सो थैंक यू सो मच फॉर योर एक्टिव पार्टिसिपेशंस। तो अब जो है क्या बोल रहे हैं, कास्टिंग कंप्लीट कर दीजिएगा सर प्लीज। हाँ मैं कास्टिंग करूंगा। आई विल कंप्लीट द कास्टिंग, डोंट वरी डोंट वरी डोंट वरी। मैं क्या भाग के जा रहा हूँ, मैं तो आपको बोला ही हूँ ना। मैं तो मेटल कटिंग कंप्लीट किया हूँ ना। आई हैव कंप्लीटेड metal cutting. I will complete casting. I will complete casting. Okay. And see, if you are planning for the plus subscription, go for the code SIRVK, SIRVK. अगर प्लानिंग कर रहे हैं प्लस सब्सक्रिप्शन के लिए, या आपका कोई दोस्त, कोई पीयर्स, एनीबडी इज प्लानिंग फॉर अ प्लस सब्सक्रिप्शन, यूज माय कोड SIRVK and you will get a 10% discount. So thank you so much, and I'm going to end this session. Okay. Any doubt? Then tell me. Otherwise, I'm going to end this session. Okay. Okay.